In this video, we'll begin our discussion of section 14.3. This will be double integrals using polar coordinates. I know you're super excited about that. So let's talk about relating this back to the rectangular prisms that we do in 14.1, talking about the definition of an integral of a surface using double integrals, right? Trying to find the volume. Let's talk about how polar coordinates are defined. So I'm going to draw just an axis here, right? X, Y. And we get these polar coordinates here. What we get is we get like this R, and we'll call this like R equals A, and then we could have this other R equals B, right? And then let's call this theta equals alpha. Then I could take another sector of this, right, cutting that, and I could use that same A, and I could use that same B, cutting that up. This is, remember how my polar coordinates work is we have an R and then we have an theta. We pick R and then it makes a theta. So we had theta there, and we'll call this second theta B. That's that angle, right? This is that. That's alpha. This is beta. So we can actually create what are called polar rectangles. They're not actual rectangles because we have curves on the edges, but in polar coordinates, this is what we're going to call rectangles. So just like in 14.1, how we built rectangular prisms, we build it the same way, this way going up. It even allows me, if I wanted to, I could draw the exact same picture, and we could even put functions there as well. So I'm going to do that here. All right, we have our first measure, our second measure. Sorry, trying to go straight. My hands are sticking to my iPad. And then let's say they weren't nice even, like this was from A to B, right? Let's say it was a different function. We'd call this R, but we'd call it G1 of theta, meaning it's some R based on theta. I could have some second one too. And we said this R is G2 theta. All it's saying, and this would still be theta equals alpha, theta equals beta. We could create rectangles this way, just like we did in 14.1 of creating rectangles to go about this, right? We could create a bunch of little actual polar rectangles that would fill in that area as much as we could. Now, there's a couple things that we need to talk about. We do get, let's go ahead and make a note here. This is polar rectangles. I want you to notice one thing. When we're doing, why this method is great, the angles remain constant. This is going to make our lives easier, and this is why polar is extremely helpful, is because one of our bounds will be R, that changes, and then the other one will be theta, and theta will not change. And you'll start seeing why this is helpful in some scenarios. Okay, so let's talk about the integral now over that function. We have this dA, and actually what happens is we can convert our x's using polar. R cosine theta, that's how we convert x to that, right, to polar. And then R sine theta. Then we have the special relationship between x squared and y squared. That gets us the r squared. That's just the Pythagorean theorem. And then we also have tangent of theta equals y over x. These should all be familiar from graphing and polar in Calc 2, and some with cylindrical. All right, so this gives us two statements. I forgot to mention what dA is. This is going to feel extremely weird. We're not going to know why until later. And just trust me that we will get to it. dA is r times dr times d theta. So we get r dr d theta. You will, at some point, and I hope you prove me wrong, will forget the r. I still do it every once in a while. In class, when I do it, people catch it, right? Hopefully in my videos, I don't forget it. That's why I have notes that I'm just teaching directly from that I've already done. But it still happens. So do your best to not forget that r. We will learn where that r comes from by the last section in this chapter. All right, so we have two options here. We have number one. So these are just some theorems here. We have the double integral. This is what it would look like in polar theta from alpha equals beta. That's the first picture up there. We have r equals a to b. And then we just plug in, okay, instead of, remember it was f of xy. Instead of x, we're going to plug in r cosine theta. Instead of y, we're going to play r sine theta. What this means is plug in x and y. That's what that means. Plug those into x and y. We're going to see a lot of that going forward, plugging things in, and we need to know what that means. We are just creating a middle pathway, right, to get to x and y. We then change r or dA to r dr d theta. That was that first option up here. If you want to go back up, this was number 1. Number 2 is this one. It's not much different. What's really nice here is the angles, alpha to beta, are the same. The only thing changes now is we have r equals g1 theta, r equals g2 theta, and then we still would have that plugged in. So r cosine theta, r sine theta, r dr d theta. Okay, so those are our two. These are for polar double integrals or iterated integrals. Polar double, let's call it that, double integrals. All right, so those are our formulas. We're going to get some examples in this video down, and we'll worry about where this r, this feels like random r, comes from by the end of the chapter. Okay, let's take a look at our first example and start piecing this together. All right, so we have the integral of xy dA. R is the region in quadrant 1 bound by that x squared plus y squared equals 4, y equals x, and x equals 0. You need to draw a picture to make your life easier. Okay, so this is a circle with r equals 2. So I'm going to do that. Stuck in the first quadrant, so that's why I'm only doing this quarter of a circle. All right, so that's x squared plus y squared equals 4. Then they have y equals x. Okay, well, that's one, goes through 1, 1. Right, and then the region bounding Q1, right, so that's quarter 1. We did the circle. We did y equals x, and then it says x equals 0. X equals 0, be careful, straight up and down. So the region we're looking for is right here. So we want to shade or find the volume of this z, whatever z is xy in this case, right? Z is xy, that's our surface. The air volume of under that surface caught by that region. All right, so first thing I notice, this is a good indicator. Polar leads us to circles. Anytime we see circles or anything circular, we would like to use polar coordinates. Anytime things look like a rectangle, we use rectangular. Now, we use our we know that x squared plus y squared is equal to r squared. And then if I solve for r, I get r equals 2. We don't need to worry about the plus or minus. So I know r equals 2. I also know that dA, I just write it down so less of a chance for me to forget, is r dr d theta. All right, so if we were going to set up this volume, and we do all the replacements. Okay, so it was xy, so let's zoom out a little bit. You see the xy at the top? I replace x with r cosine theta. I replace y with r sine theta. And then I have an r dr d theta. I do all that first. Now, for these, and we mentioned it above, theta will always go on the outside. Always. R here. Okay, so R runs from, okay, how we do this is we start at the origin, and the first region or curve we hit is where we start, and the last one we hit, this one goes all the way through it. It's already inside of it, so that means it starts at R equals 0. If it was cut like this, maybe we'd start whatever that R is. So it's R equals 0 all the way to R equals 2. That's what the circle is, right? We got that from here. R to 0, R is 2. Our thetas are right down the middle. You could use, if you'd like, tangent theta and try to find this point right here. Or we just need the angle. You could use 1 over 1. Well, that is pi over 4. It's right down the middle. So that's where that would be. It starts at pi over 4, and it goes straight up, which is pi over 2. Okay, so we got to start working this integral out. As we go further, I'm going to work less integrals out and just give you the answer. This is to keep videos decently short because these sections start getting really long. In this problem, we will not do that yet. So theta is pi over 4 to pi over 2. Let's take our middle integral, or let's rewrite it actually probably first. R equals 0, r equals 2. We get r cubed cosine theta sine theta dr d theta. R cubed. Now, what's really nice about this is that we get to take our integral with respect to r, which means, well, we only have one r on the screen. It's r cubed. So this is r to the 4th in the argument, not on the screen, in the argument, over 4, cosine theta sine theta. And then this is why we write down r's, r, the equals things, right? R equals 0 to r equals 2, d theta. All right, I can drop the thetas because they're going to go away. Pi over 4 to pi over 2. We plug in 2, and we get 2 to the 4th is 16 divided by 4 is 4. Cosine theta and sine theta do not have an r, so I don't plug them in. Minus, if I plug in 0, it's going to turn it all to 0, so that gets me d theta. At this point, if you wanted to, you could plug this into a calculator. A TI-30XS or anything like that would be just fine. I don't really care at this point. This is a Calc 2 problem, but I do want an answer, so you either do it by hand or in your calculator. This is a u sub. Let u equal sine. Du is equal to cosine theta d theta. So that takes care of the d theta. I get a 4. Let's go ahead and change these to u's. Okay, sine of pi over 4 is radical 2 over 2. Sine of pi over 2 is 1. Then I get cosine and this d theta are gone for du. Sine is u, so I get u d theta, du. So I get 4 u squared over 2 from 1 to radical 2 over 2. Just plug it in. Okay, so plugging the 1 in, we get 1 squared over 2. 4 over 2 is 2. We plug in the radical 2 over 2. We get 2 over 4, which is 1/2. We get 1/2. We get 1/4. I think, right? Square root of 2 over 2 squared times 1/2. That's how I would think about it. That's that over 2. So we get 2 over 4 times 1/2. Okay, which is 1/2. 1/2 times 1/2 is 1/4 times 4, which is 1. So our answer is 1. All right, you can use your calculator if you'd like. That is perfectly fine at that point. I just want you to put the integral together, take the first integral, and then you can use the calculator on the second one. All right, got a couple more for you here. So it says find the volume between z equals 0 minus, I think that's supposed to be a 9. Wouldn't make sense for it to be a 0. Okay, 9 minus x squared minus y squared, and the xy plane is bound by the cylinder x squared plus y squared equals 1. All right, so let's first draw a picture. All right, I know that shape here. That's a circle with radius 1. All right, so it's in that. This tells me that polar probably is going to work very well. So I take x squared plus y squared, since that's equal to 1. I can actually change that to r squared equals 1, which tells me r is 1. The region I'm trying to find is the whole disk, right? The whole circle interior. So if I think about r, what does r start at? It's going to be, okay, well, let me finish filling this in. Good enough. We'd start here going out. Well, the first thing it touches is the second curve, so it started right in there. So this is from r equals 0. So that's this r equals 0. And I guess let's do it the other way. It makes more sense. Sorry I wrote a 0 there earlier. That was supposed to be a 1. So we get from r equals 0 to r equals 1. Sorry for writing so much there, messing that up, but there we go. So we know our r's. Let's take our surface for a minute. Z equals 9 minus x squared minus y squared. Notice we can make some replacements here too. This is 9 minus, if I factor both of those out, they can be positive. That tells me z is minus r squared. I have almost everything I need. Okay, so I want the volume of this thing. The thetas are always the same, or constant. They don't change. In this case, since it's the whole disk, it's 0 to 2 pi. Let's fill in this was what we are changing, which changed to this. That was our argument, our surface. So I get 9 minus r squared. This is the part that people forget. I get r dr d theta. We introduced the r. We already discussed r's. R's is from 0 to 1. Starts in the circle. That purple thing there that I have the perfect arrow right here, purple arrow. Can't talk. I apologize. All right, we got to work this out now. All right, so I'm going to start writing small. I'm running out of room. Theta equals 0. Theta equals 2 pi. We can go ahead and take our integral there. I'm going to write it in here, 9r minus r cubed. So this is 9 over 2 r squared minus 1 over 4 r to the fourth. Ooh, we can't do that. Actually, go back one more. Oh, no, I multiplied by the r. Forgive me. Okay, we're good. We multiplied by this r. I thought I forgot it for a moment. Then we have dr. We just did that integral, so we're left with d theta. We did the integral of this part right here. That was the distributing, and then we did it with respect to r. R goes from r equals 0 to r equals 1. That leaves us with, well, I only have r's, so 0 to 2 pi. All the r's go down to, if I plug all that in, I get 17 over 4. Right, this was the same thing as 0 to 2 pi. Plugging things in, we get 9 over 2 minus 1 over 4. You need that intermediate step. We're here now. This makes this nice and easy. 17 over 4 theta from 0 to 2 pi. The 0 is going to make that one go away. So we get 17 over 2 pi. So that is the volume under that surface using polar coordinates. So it is much quicker. I would encourage you, if you want to, try to do it in rectangular and see if you can get the right answer. It could be quicker. Sometimes these are, sometimes they are not.